So I'm going to tell you a bit about some of the history of women in tech. I guess the best way to start is back about 15 years ago or so. I was sitting in a dorm room in college, and I was just like, well, I'm the only female in a bunch of my classes. And it was engineering classes, business classes, math classes, and I'm just like, why am I the only one? And I couldn't be the only one who'd be interested in this. And in future classes, I would notice there's always that one girl. Like, really? And so I had to wonder, first of all, was there ever women in technology who made some significant contributions who we could use as role models? And so I ended up doing some research online and found all sorts of contributions in all different parts of the industry. And so today we're going to talk about some of the ladies who did make an impact to the technical world. We'll talk about Ada Lovelace. We'll talk about the ladies of the ENIAC. We will talk about Grace Murray Hopper. Talk about Barbara Liskov, Frances Allen, Mary Lou Jepsen. We're going to start, though, of course, with Ada Lovelace. She was born in 1815. Her name was Augusta Ada Byron, Lady Lovelace, but we commonly know her as Ada Lovelace. She was born to the famous poet Lord Byron. Shortly after she was born, though, her parents separated and her mother raised her. And her mom did not want her to turn into the poet that her dad was. She was just like, no. And so back in those days, mathematics and sciences were traditionally considered a male's topic. And the ladies just would not do that. They were trained more for society appearances and for taking care of things at home. But Lady Byron wanted to make sure that her daughter had skills that would steer her far from that whole poet imagination side. So she thinks, well, let's get her tutors in math and science, and maybe she'll just stay away from that. In 1828, while she was playing around with something, she ended up drawing a flying machine. And I'm sure her mom saw whatever she was drawing, like, oh, that's pretty cool looking. It's not poetry, so this is good, right? But at the same time, when you're born from parents with that kind of talent, you can't neglect it. And so she asked her mom, she's like, if you can't give me poetry, can't you give me poetical science? We're like, poetical science? What is that? And it's just one of those, because she was born to a creative person, she happened to have that creative mindset that I want to do something really awesome and put my creativity into it. And so it was one of those, how could she do that? So her mathematic mind, because she was tutored in math, she just couldn't help that math mindset. And I'm sure plenty of us here can also relate. I'm definitely one to say I understand where she's going with that. But then she had this runaway imagination. I mean, come on, drawing flying machines? That's pretty cool. But that's also going to take a lot of imagination. And she also liked to talk about mathematics and metaphors. And so we've got something pretty analytical, pretty straightforward, cut and dry. Plus then you get the creative side. That doesn't sound like it's a good combination. And then you get metaphors, which is like, oh, crazy confusion. But for Ada, that was magic. For her, that was her world. That was what she lived in. And she only lived till she was in her mid-30s. She unfortunately followed in her father's footsteps in that kind of path as well. But in that short amount of time, she was able to contribute a lot more. So when she was 17 years old, through her friend Mary Somerville, she met this man here. This guy is known as Charles Babbage. I'm sure if you've been in the industry long enough, you've heard of him. He did the difference engine, the analytical engine. But Ada studied under him. And what was nice with him, his background, so he's got mathematics, he's got philosophy, he's a mechanical engineer, and he's an inventor. So he's got similar mindsets to her, so that made it even easier for her to learn from him. And Ada did have a life outside of just studying from him. As she grew older and as she would get married and have a family, She also was socializing with various people of the times. So it wasn't just she was studying under this guy. She also had a life. It's like both of us here. I mean, we're here learning about programming languages and the awesomeness that happens in our community, but then we go home, and while we're still doing this kind of stuff, we also have our families or other things. So Ada had this kind of similar, what I like to call sometimes a normal life. So she's the wife of Earl Lovelace, and at one point she had 3 kids under 8. That's a handful. Mind you, while she had these 3 kids under 8, she didn't give up her career. She was still working with Charles Babbage on the stuff that he was studying at the time. So she was juggling both career and children. In 1843, she was still working with Babbage, and she had some ideas for his analytical engine. And some of the things that she predicted what they would eventually be used for include things like compose complex music, or produce graphics. And then eventually that will be practical and scientific use. 1843. Here we are today now in 2013, and we have computers that do that. But this was the long predecessor of computers. And if they could predict what we're doing now, back then, I can only imagine what we're going to be doing in the future. But these are Ada's predictions. So she had that imagination, that insight, and now look at where we're at today. To have that was pretty cool. In terms of what she did with the analytical engine, she documented it for Babbage, and she included the first, what is considered the first program. So basically what she did is she showed how to calculate a sequence of the Bernoulli numbers using the engine. This is part of her documentation. So the first computer program was documented. How many of you guys have actually seen code documented so nicely? I mean, where we're at today, how many of you guys run into these things where you're using code and you're like, well, there's no documentation for that. Well, I got to see how this is going to work. Oh, I hope this works like it's supposed to. But she actually documented it, so there was none of that mystery. It was pretty cool. And then to be able to add her own words to it, it's a significant contribution. And she was the first individual to create a computer algorithm. When you think of it that way, it's on paper, it's proof. That's pretty cool. In 1843, she published in the English Science Journal with just her initials, but they were able to prove that it was her. But she did it on how codes can be created to handle letters, numbers, and symbols. Well, if we can change all those into code, then use it on this analytical engine, sounds like we got programming. So some of the things we can learn from Ada. Follow your passion. She got her poetical science. She was able to put her imagination to use, and it led her to create a computer program. I mean, nowadays we write computer programs, and for some of us it seems so natural. But for her, she did it. And not only did it, but documented it to where people could actually follow along and understand it. Something else we can learn is that moms can work while maintaining a social life and a career. I mean, she was still socializing with friends while she was creating this documentation. And at the same time, 3 kids under 8. I mean, seriously, how many of you out there are parents with 3 kids under 8 trying to juggle your family life, your career life, and a social life on top of that? It's pretty significant. And then choose a mentor who you're interested in learning from. As Ada did, she found somebody who had the passion that she had, but had the experience that she didn't have just yet. And she was able to not only learn from him, but she was also, there were documents of her and Charles Babbage going back and forth on these things. And with her excitement for it, he was able to feed off of that. So he would get excited about it, and then she'd get excited, and then he'd get excited. And so not only did she have a mentor she could learn from, but she could take in from his excitement and his energy and also contribute back. Which is a good thing in a mentor relationship. If you can contribute back, I mean, everybody wins. Now, after Ada, we had this thing called the ENIAC. And it was a huge, huge computer thing. It took up a large amount of space. And these are some of the pictures of some of the ladies that are involved with the ENIAC. And I've talked with some of my friends, and they're just like, oh, we see these pictures. Were those like some ladies who just happened to volunteer there? No, they were actually people who worked there. These are ladies who actually wrote the programs, who also, they documented their stuff too. So again, documentation. This is more the ENIAC, of course. As you can see, lots and lots of cables, lots of knobs and tubes. And if you haven't seen the ENIAC, it's phenomenal to see. I had a chance to see it when I was in DC a few years back at the Smithsonian. And so to see all the knobs and tubes and the dials, and to see where computers went from there to where we're at today, I mean, I'm presenting on a Surface Pro, so we're talking little guy. So to go from that to this, phenomenal. So we're going to take a look at some of the ladies who were involved with the ENIAC. We're going to start first with Kay McNulty. She is one of these ladies here in this picture. There were 6 original programmers of the ENIAC. She's one of the original. Her background was in mathematics. Now, this is something you're going to see that's pretty common throughout all the women in tech, is that they have some kind of scientific or engineering kind of background. So we've got mathematics here. She started with ballistics trajectories and then just happened into the ENIAC. They had said, okay, we need you to go on to this project, and it happened to be where the ENIAC was. After the ENIAC, she ended up working on the BINAC and the UNIVAC 1 software design. So she stayed in the computing world. And eventually, she would marry one of the ENIAC co-inventors. And I have to point that out. There are times where you are going to run into somebody in the field who might be married to somebody else in the field. I've met people who are like, well, we're not too sure of mixing or bringing the same people. It's going to be weird fights. But for them, it really worked because he would encourage her to continue down that path. Then there's Jean Bartik. And she's in this picture, actually. So there were 2 people, she and this other programmer, which we'll talk about here in a little bit. They were responsible for administering the master programmer. They called it the master programmer. It was the central spot for the ENIAC code. So it was like essentially the main core of the ENIAC. They helped transform the ENIAC into something a little bit easier to work with, and they helped make it a little more able to handle more sophisticated problems. So of course, the ENIAC that they got was primitive, and they found ways to improve upon it, and weren't afraid to make suggestions on how to improve it. Again, after the ENIAC, she too moved on and stayed in the computing world and went to BINAC and UNIVAC 1. Marlyn Mescoff-Meltzer, she's also one of the original ENIAC programmers. She was hired, before the ENIAC, she was hired to do weather calculations. So weather calculations, and then she also moved into ballistics trajectories, and then moved into ENIAC. So this is another pattern that I noticed with the ENIAC women, at least for that time. So we're talking back when this was here, ballistics trajectories and other mathematic computations like that were common. And so you're going to see that with a lot of the other ones. They all have this ballistics trajectories example. So we've got Betty Snyder Holberton. She's in this picture as well. She's the other one who was responsible for the master programmer. It took 2 of them to wrangle this thing. She moved on to become part of the UNIVAC 1 code team. She also became part of the COBOL committee. We'll hear more about COBOL later. She also worked on developing standards for FORTRAN, which we'll hear a little mention of FORTRAN later, too. So we're talking, they went from the old technology to a computer that took up forever amount of space to slightly newer technology, newer compared to the ENIAC, and a lot more improved, a lot less shorter, and probably a lot less work. Fran Bilas, her background was in math and physics, and also worked on ballistics trajectories. All these ballistics trajectories. And she was also one of the first ENIAC computer programmers. Not really documented too much as to what was going on with her. Ruth Lichterman, her background was in math. And after the ENIAC was done in its initial assignment, it got moved on, and Ruth followed along. And Ruth had a job that I imagine if I were alive back then, I would hope to have something similar. Her job was to teach future programmers how to actually work with this beast known as the ENIAC and how to improve upon it. And so I think that's pretty cool that they were trying to keep the technology going and bringing up the next generation. Now, Adele Goldstine, make sure you guys know her name. She was the one who was responsible for training some of these ladies who are doing ballistic trajectories. She was training them on calculating the firing table trajectories. So again, those trajectories just don't go away. But she wrote the documentation for the ENIAC. We're talking documentation again, something that we in modern day programming don't always see. Back then, they actually did it. And she created this report on the ENIAC to explain the ENIAC as to, number one, how is it built, all the way down to the resistors. So we're talking the electronics behind it, and then how do you use it as well. These two ladies here are not part of the original 6. They were part of the next class, the next 100 programmers. But as you can see, there were still women who were doing programming on this crazy ENIAC. And I say crazy because the intensity, the length of it, the amount of work that you had to do behind it was a lot more than just the simple, okay, let's type a couple letters here and there, let's add a semicolon here, curly braces there. It was more like we got to wire this stuff up. And I love this quote. When I saw it, I was just like, this is crazy to think about. But when you think about it, the ENIAC had a calculator with 18,000 vacuum tubes and weighed 30 tons. 30 tons! I mean, how many of you guys are going to put a 30-ton machine in your back and then haul it down to the conference center? It just doesn't happen. And then they hope that maybe one day computers will only have 1,000 vacuums and weigh 1.5 tons. This was 1949. 2013, our computers weigh a lot less than 1.5 tons. So I hope that if they were still alive, they could see that change. Because how many of you guys really would want to be hauling around 1.5 tons of computer? Yeah. All right, the next lady I want to mention is Admiral Grace Murray Hopper. Now, leading up to today, I had been running into people, be it at the hotel or when we're out, and they're like, Sarah, are you going to mention Grace Hopper? Are you going to mention Grace Hopper? I'm like, are you guys really asking me this question? Because the thing is, if you don't know about Grace Hopper, well, first of all, you're in a good spot. I'll tell you all sorts of stories. But second of all, I mean, her contributions are so significant that even in college, I knew of Grace Murray Hopper and her contributions. It was one of those, I can't hold her back. I can't leave her off of this list of women that were visiting in tech. She enjoyed tearing things apart and learning how they worked. I'm sure, how many of you guys do that? I should see a bunch of hands up. I mean, we're programmers. We have to tear things apart in order to write our programs to make them work properly. So Admiral Hopper, her background was math and physics. Of course, she went all the way to get a PhD in mathematics. And then she went into teaching. But her family background was military. And so while she was teaching, she eventually decided she needed to move into military and join the Navy. And she was part of a group called the Women Accepted for Voluntary Emergency Service, or WAVES. And 6 months after enlisting, she was commissioned as a lieutenant. Now, this is a statement that she just really did not like hearing. How many times have you gone into a company and you've looked at the stuff that they're giving you and you're like, but why are you doing it this way? And you hear this line, we've always done it that way. We've always done it that way, so we have to continue doing it this way. Grace Murray Hopper did not like that line at all. To her, it was one of those, so you've been doing it this way all along, why? There's a better way, or an improved way, or a different way. Let's take a look and see what those are. She did not like this line, and rightfully so. If you get stuck doing the same thing over and over and over again, progress doesn't necessarily happen. It's like doing the same thing over and over and expecting different results. So she ended up going on this trail of success, as I call it. She started in her military career. She had a compute coefficient to arctangents on a Mark I. Basically, what happened is when she enlisted and showed up, the guy who was running the project was a fellow professor, and his line, and pardon my language, this is exactly what they asked, was, "Where the hell have you been? I need you to go compute those coefficients." I mean, to have that kind of welcome, he already knew of her success as a PhD and a mathematician, but I think he was more excited that she was helping with this. She created the 500-page manual of operations for the automatic sequence-controlled calculator. Documentation again. I mean, seriously, this is awesome. And she eventually moved on to the Mark II and the Mark III, so she worked in the Mark series. She not only did the programming behind it, she also documented it. And then she became to this point where she was on this quest. I call it a quest because I play a lot of computer games and video games, and they all have quests. And so I see life as there's a quest. And she wanted to find programmer-friendly and application-friendly tools. Her thought was, why do we in the science world have to be the ones who have access to this and nobody else have access to this? She wanted it so that computer could be to a much wider audience. Part of her adventures, so she went into private consulting for a little bit. And the company where she was at, she wanted to increase collaboration. And so they ended up writing code and talking with each other and sharing their code. Ran into the whole, it reduced the errors, it was less tedious, there was less duplication of effort. They actually worked as a team. They had really good team chemistry to make things very successful. So to see that kind of collaboration getting encouraged early on, it's always a good thing. She did a lot of significant contributions to the compiler. The compiler had a bunch of mnemonics that they transformed into binary coded instructions. That way, once you have it in binary, you can easily then transfer it over to the computer. Her first compiler that she created was the AO series, and it allowed us to set call numbers for routines and then access those routines from the call numbers. This was the compiler in the AO series, and I'm sure if you deal with compilers today, you know how advanced they've gotten. But again, she wanted to reach out to the non-scientific reaches as well. She figured, well, we can open this up to the world through programming languages, through refining what ones they were already using, and also developing new ones. So there was this thing called Flowmatic. And yes, that's a screenshot of the Flowmatic code. It looks like it's written in plain English. I mean, you see things like input inventory, file A, price, file B, output price. And so this is, I guess the best way to think of it as programmers is it's pseudocode. But for them, this was their actual code. And it was used to work with automated billing and payroll calculations. So we're moving out of the science realm and into business. And what happened with Flowmatic and with Admiral Hopper's contributions is that eventually the UNIVAC 1 and the UNIVAC 2 understood at least 20 English statements. So this Flowmatic with this like rewind and read item and write item, that's all English. That's stuff that no matter what programming language we write in today, if you can see this, you can probably write this in your language. But this happened to be the language that they used for UNIVAC 1 and 2. In 1952, Admiral Hopper published her first compiler paper. Moving on, we've got COBOL. Admiral Hopper was also involved with the COBOL language design team. COBOL, if we go back to Flowmatic, pretty English looking. COBOL, pretty English looking. Was greatly influenced by Flowmatic. It was defined by the Conference on Data Systems Languages, or CODISL, their executive committee and what they call their short-range committee. The first specs came out in 1959. And then there was a big push for standardizing COBOL. And Admiral Hopper, not only was she tech-minded and had that background in mathematics, but she wanted to reach out to the people. She also had that inner ability that some of us don't always have, where she could market it well. So the companies that she would be working with, she would work with them, including the Navy, on actually adopting COBOL. So if any of you guys are still working on COBOL projects today, you can blame her. She did a good job marketing the language. And so people did start adopting the COBOL language. Through her changes, she also would push forward language validation. Started with COBOL, and then other programming languages and platforms also got it. That led to national and international standards. Now, Admiral Hopper, obviously, as you're seeing, a lot of significant contributions. She also taught for the United States Naval Reserve while doing all this work. So she's run the whole gamut. She's done the military side, she's done business, she's done academia, she's done private world. So she's very well-rounded contributions. She retired from the business world in 1971. I use the word retired loosely because she continued to work in her 80s. She stayed in the military, of course. She was promoted to Commodore in 1983. A couple years later, the Rear Admiral title would merge with the Commodore title. And so then she became an Admiral. She retired from the Navy in 1986. Now, somebody looking at the slides, I just have to make it clear, the only reason why I didn't capitalize Commodore is because I didn't want anybody to get confused that she was promoted to a computer position, not that Commodore. In 1992, when she was buried with full naval honors. So her military pride that lasted all of her life continued to follow her through her death. And so some of the things that she had award-wise, in 1969, she got the Computer Science Man of the Year award. And I imagine if she were around today, she would probably still respond to the, hey, you guys, and not be offended. I mean, at that point, it is what it is. 1971, a company that she worked for, Sperry, they created an award in her name. In 1973, she was the first American and first distinguished fellow of the British Computer Society. And these are just some of the awards. She has all sorts of awards, all sorts of accomplishments. There's a Grace Murray Hopper conference that ACM runs. So she's very well known. I mean, her influence, as you can see, in all different things for the different aspects of computing today. Be it from code optimization to compilers to doing any kind of like modeling with the symbolic manipulation. And I only put a few things on this slide. The list of her contributions would fill up that slide and more. So some lessons we've learned from her. Just because we've always done it that way doesn't mean it's right. Don't be afraid to challenge those words. Programming works well as a team task, especially when collaboration happens. And when you bring it down to plain English, computing is not just for programmers at that point and for mathematicians. It's a lot more approachable. So it doesn't have to be so scary. That's Grace Murray Hopper. Next thing we're going to talk about is not the solid principle. You can ignore that part of the slide, except the orange box. That's the Liskov substitution principle. Liskov, that's a woman in tech. That's Barbara Liskov. She got her PhD from Stanford. She was the first woman to get a PhD in computer science from Stanford back in 1968. And her main focus was computer design and operating systems. She has received the ACM-AM Turing Award for her work in languages. One of the things she did is she created this Venus computer system. It allowed her to construct complex software. What was unique about it is that it, at the time, allowed 16 teletype connections, and everybody was working in virtual machines. So the reason why she decided to go with virtual machines is, let's say that this gentleman here, that gentleman there, that lady there, are all coming into the Venus system. Well, if this guy here happens to write a system or an error message, or something that causes the system to die, he only messed his virtual machine. He didn't mess up with that guy or that lady's VMs. So we had virtual machines on this thing. We're not talking like VMware, Hyper-V, any of that stuff. We're talking back in the day, virtual machines. She also worked on teams, she led teams at MIT for the CLU programming language and the Argus programming language. And if you haven't heard about them, if you are an ACM subscriber and have the digital library, this is from March of 1988. So CLU, its strong things are modular programming, data abstraction, and polymorphism. So what we see in languages like C# and Java, older languages, much older languages had these, and those have been carried forward. Now they don't, the CLU and Argus, being older languages, don't have a lot of the modern day features, but to have this kind of stuff back then was neat. Argus was mostly focused on distributed applications, nested transactions as well. This is Dr. Liskov, and these are just some of the things that she's interested in focusing in on, from garbage collection to caching, fault tolerance, security. So she's all over the board as to what she's interested in and what she's contributed to. The MIT president has talked about Dr. Liskov being revered in the MIT community because of all of her contributions to computing. She's not only a scholar, but she's also a mentor, be it to other faculty members or also to her students. She's also a leader. I mean, the work that she's doing is innovative, it's creative, and it's pioneering. It's the way that she's leading it. As the MIT president continued, her pioneering research has made her one of the world's leading authorities on computer language and system design. And that's pretty neat. Now, Fran Allen. Fran Allen's known for her compiler contributions and also dealing with parallelization. So parallel computing, let's keep it easier to say. She has worked with the NSA on programming languages and security codes intelligence. I don't know if Edward Snowden leaked anything that she worked on, but in 1989, she became the first female IBM fellow. She also became the first IBM Academy president. Now, IBM was where she figured she was just going to start, pay off her college bills, and be done. And she stayed her whole career there. So she did really good there. She also received an AM Turing Award in 2006 for her performance in improving performance. She's got a lot of different published works, as we can see here. She did programming optimization. She did the basis of program optimization. She's dealt with a lot with the compiler stuff. She worked with a gentleman named John Cock on making things work with the compilers and compiler optimizations. She also worked with FORTRAN and being able to run FORTRAN in parallel. So if you've ever heard of PTRAN, she's the one to blame. She did the new parallelism detection schemes and made FORTRAN a lot easier to run, to handle parallel jobs. Now let's go a little bit further with Lou Jepsen. She's a little more modern day than our Ada. So her background, she's got the electrical engineering, so the engineering part I would expect. She also has studio art. So she's got the analytical mindset and the creative mindset, which we saw with Ada, led to some pretty outrageous things, wouldn't you say? To make this even more interesting, she's got her master's in holography. And holograms, really? And then a PhD in optical sciences. So we've got holograms, we've got optical sciences. This could only lead to some crazy fun stuff, right? Well, nowadays she's the head of the display division at Google X Lab. That's Google's top secret lab. Why we're calling it top secret when we're actually talking about it, I don't know. But that's their lab. She's the founder of Pixel Qi, which is known for their low-cost, low-power LCD screens, which is pretty nice to see. And she's also the co-founder of One Laptop Per Child. How many of you guys have heard of One Laptop Per Child? It's good to see this many hands. So One Laptop Per Child, basically their goal, of course, is what the name suggests. They want to do laptops per children. They are deployed in over 50 other countries besides the US, or in addition to the US, in more than 25 languages. Every child in Uruguay happens to have one of these laptops, these XO laptops. They have sunlight-readable displays, so those Amazon Kindles and those iPads and stuff, this stuff is actually a lot easier to read. They're ultra-low power management. What's nice, too, is they're also the most environmentally friendly. I believe that I was reading those 5 carbon steps. But this is what she did. She was a co-founder of One Laptop Per Child. You can see her contributions in various things, from holographic video to projectors to HDTVs to head-mounted displays. Now, I'm not saying that she contributed to Google Glass, because I don't know where she's at in the Google X labs. But this screenshot here of a head-mounted, so it looks similar to a Google Glass, was something she worked on for another company. And this is taken straight off of her website. So if she was doing that for someone else and now she's in Google, it would be cool if she were working on glass with that kind of background, wouldn't you think? I mean, what do you guys think? Yeah, here's some yeahs in there, that's good. So these are just a few of the women that are in tech, but there are so many more. I mean, we've got Meg Whitman from eBay, from DreamWorks, Hasbro, now she's at HP, so she's making her rounds in executive positions at these tech companies. Mystery Warrior is currently at Cisco. She was at Motorola. Again, another powerful woman in tech. Anita Borg. So she's more known for bringing non-tech women into the design realm because they have a different mindset. She's also she was interested in promoting women more and getting more women in the tech world. Because if you think about it, there aren't that many here. And not saying just here at Strange, but here in the tech industry as a whole. Ernest Snyder, she invented computerized switching for telephones. This technology, when she invented it, was revolutionary. And here we are many decades later, and it's still being used. Then Jean Sammet, she came up with the format programming language for symbolic manipulation of math stuff. These are just a few more of the ladies that I happen to squeeze into my presentation. But if you do a search in your favorite search engine for women in tech, the list nowadays is endless as to who's there and what they're doing. So while there are a few of us out there who are actually talking about it, there are a lot more who are actually doing things. But there's still not that many. We need to promote more, bring more, tell people how much fun it is to actually do this stuff. So some of the lessons we should learn from the women that we talked about today. Based on Ada's experiences with Charles Babbage and his analytical engine, this applies to everybody, not just women in tech, but choose a mentor who you're interested in learning from, and both feed off of their energy, be able to contribute back to encourage that energy. That helps to bring a really good relationship, and it brings not only you as the mentee forward, but it also brings your mentor forward as well, because it challenges them, keeps them on their toes. Through the women of the ENIAC, keep an open mind about your career, because you never know where it's going to end up. I mean, you go from ballistics trajectories to the ENIAC, to the BINAC, to the UNIVAC 1. For a lot of them, they stayed in computing. For me, I went from tech support to IT database administration and system administration to development to wherever I choose to go today. So, I mean, keep an open mind. You never know where that path is going to take you next. Based on Grace Hopper, make tech more approachable by translating it into plain English. So if somebody comes up and asks you, what do you do? You write programs. What does that mean? Don't say, oh, I write curly braces and semicolons, and don't whittle it down to just magic. Put it in plain English as to what it is we do, because then people get more curious. If they can understand what we do a little bit more, they'll ask more questions. Then they'll probably want to get involved in the field a little bit more. It'd be nice to see a lot more people getting involved and actually getting into our field. And then finally, challenge that we've always done it that way. If there's anything you've gathered out of my talk, make sure that next time you hear we've always done it that way, to question it. Ask yourself, we've always done it that way, but why? Why do we need to do it that way now? When I can see this more efficient way of doing things, or this better way of doing things, in one form or another. Don't be afraid, because if you don't take that risk, you're going to get stuck doing the same thing over and over, and we might not necessarily progress. So these are some of the things we've learned from the women in tech, and I hope you enjoyed our adventures here. If you have any questions, please feel free to find me here at Strange Loop. Thank you, guys.